Hello, and welcome to the lessons developed as a part of TRACE project. This presentation provides a synthetic analysis of how coastal environments are vulnerable to climate change-related hazards and risks by integrating conceptual framework, methodological approaches, and policy-oriented adaptation strategies. Here is a quick overview of coastal environments to highlight why recognizing and reducing their vulnerability matters. Coastal zones are highly dynamic interfaces between land and sea, marked by strong interaction among geophysical, ecological, and socio-economic processes. They include diverse landforms such as beaches, dunes, cliffs, deltas, and estuaries, along with sensitive ecosystems like mangroves, wetlands, and coral reefs. Additionally, they are heavily populated and support major economic activities like ports, tourism, fisheries, and energy infrastructure. According to official statistics, about 33% of the world's population lives within 100 kilometers of the coast, and 15% lives in extremely low-lying areas with less than 10 meters above sea level. And when it comes to Europe, the numbers are even higher. The COP-POP graph from 2018 show a higher number of coastal population compared with immediate inland areas, which contributes to a greater anthropogenic effect on these environments. Coastal areas perform many key functions, such as regulating water exchange between land and sea, controlling the chemical load of sediments and water, storing and recycling nutrients and human waste, maintaining biological diversity, offering transport and tourism opportunities, and supplying information on aesthetic, historical, cultural, and scientific aspects. So, living near the coast offers many advantages, but it also exposes inhabitants to various hazards related to sea level rise, stronger storms, coastal erosion, and saline intrusion. Sometimes exposure to multiple hazards at once is common. The occurrence of these natural events is beyond human control, though human activity could intensify their effects. At the same time, people living near the coast often cannot cope with these hazards, which makes them vulnerable. Global assessment highlight that coastal areas are already at risk, and it is expected to worsen under all future warming scenarios, especially for low-lying deltas, small islands, and heavily populated urban coasts. I have already mentioned some concepts whose theoretical content needs to be clarified, such as hazard, vulnerability, and risk. These terms are commonly used, often interchangeably. However, it is essential to distinguish between these two and other related terms. While hazard refers to a physical or man-made process that can cause harm to humans, risk includes also the probability that the hazard will occur and its possible consequences. For a better understanding, let's take the example of two men crossing a street. One passes by pedestrian crossing, while the other crosses through other places. For both, the risk of being struck by a car exists, but it is higher for the person who doesn't follow the rules by crossing randomly. Therefore, risk also involves a behavioral aspect which describe vulnerability. So, contemporary research includes vulnerability within a broader risk framework. At global level, some international programs aim to promote common understanding and consistent use of risk-related concepts, such as United Nations International Strategy for Disaster Reduction and the United Nations Environment Programme. They express risk as the interaction of hazard, exposure, and vulnerability. Hazard is described as a dangerous process that may cause loss of life or injury, social and economic disruption, or environmental damages. Exposure refers to people, property, systems, or other elements present in an area prone to hazards that are subject to potential losses. Vulnerability expresses the degree of these losses. For methodological purpose, at European level, the informed model was adopted, which balanced two main forces, the hazard and exposure on one side, the vulnerability and coping capacity on the other. So there are two forces, but three dimensions, divided into several categories and subordinated components, as is shown in this diagram. Each component can be used as an indicator for risk assessment. All hazard-dependent factors are addressed within the first dimension, hazard and exposure. In contrast, hazard-independent factors are divided between vulnerability, considered as the resilience of individuals, and coping capacity, which evaluates institutional strength. Let's take a look on each part. The hazard and exposure dimension reflect the probability of physical exposure to a specific hazard. There is no risk without physical exposure, regardless of how severe the hazard is. This represents what a community exposed to a dangerous event must to handle with. It includes two categories, natural hazard and human-induced hazards, with many indicators to be considered. The vulnerability addresses the propensity of an exposed population to be affected by a hazard. This includes the community's economic, political, and social characteristics that a hazard can destabilize. The concept aggregates two categories: socio-economic vulnerability, which refers more to the country's overall demography, and vulnerable groups, meaning social groups with limited access to the health care systems. The coping capacity dimension measures a country's ability to handle disasters through formal organized activities, government efforts, and existing infrastructure. It is also divided in two categories: institutional, focused on mitigation and preparedness, including early warning, and infrastructure, which reflects the capacity of system for emergency response and recovery. Going back to the concept of vulnerability. In the context of climate change, vulnerability refers to the extent of which a coastal environment is susceptible to be impacted by climate-related hazards influenced by both natural and social factors. The Intergovernmental Panel on Climate Change, shortly IPCC, consider vulnerability as consisting of three interconnected components: exposure, or elements at risk, describes the presence of people, infrastructure, ecosystems, and services in areas prone to climate-related hazards. Sensitivity reflects how much these elements could be affected. Adaptive capacity reflects the ability of ecosystems and societies to respond to and recover from climate-related impacts. As you may notice, exposure is considered both as a distinct element of risk and as a key component of vulnerability, which can lead to confusion. In this respect, a well-defined conceptual framework is essential for coastal vulnerability assessment in order to ensure a sustainable development and climate-resilient planning. First step of each assessment process is to correctly identify the determinants factors. Key effects of climate change include switch in wind patterns, rising sea level, and storm surges. For example, higher sea level increase baseline water level, rising flood risks and allowing salt water to seep into groundwater. More powerful storms and unpredictable ocean conditions accelerate erosion and increase coastal flooding. Wind patterns influence sediment movement and reshape sandy landforms. Ultimately, these changes cause shoreline retreat, degrade saltwater quality, harm ecosystems, and pose social economic challenges, even with minimal sea level rise. So, coastal hazards come in multiple forms that can be classified into three main categories as presented in this table. Natural erosion and flooding impact the sediment budget, leading to land and habitat loss, freshwater quality due to seawater intrusion, property and infrastructure damage. Sea level rise and climate change increase ocean water volume with a global average of 3.3 millimeters per year, affect freshwater aquifers, reducing availability of water resources for human use, alter salinity in estuaries, affecting flora and fauna, and accelerate erosion rates and flooding frequency. Human-induced coastal threats alter natural shoreline processes and topography, while water pollution causes eutrophication, algal blooms, and harms marine life. It appears that coastal vulnerability is shaped by the interaction of geophysical processes and socio-economic conditions, with the main susceptibility referring to coastal erosion dynamics, habitat degradation, sediment transport disruption, biodiversity loss, and infrastructure vulnerability. Here is an example from Naxos Island in Greece. It is a steep coastal area, a cliff that rises with 30 meters above seashore, and it is prone to landslides due to its geological and geomorphological features. However, the same features, offering a prominent position above the sea and a broad perspective towards horizon, were considered attractive by some members of the community. So, they began to expand the street network, and more houses were built right on the edge of the cliff, ignoring the threats posed by gravitational processes, which, as observed, are quite active. Moreover, these constructions exerted additional pressure on the sedimentary rocks due to their weight, increasing the risk of landslides. Soon after, cracks and bulges start to appear, affecting both roads and houses' walls, and forcing the owners to abandon them in order to avoid danger. As you can see, coastal erosions becomes a hazard when society fails to adapt to its effect on people, property, and infrastructure. Many human settlements are built in areas vulnerable to coastal erosion, with early estimated suggestion that about 70% of the global coastline is affected. Understanding exposure to climate variability needs to address episodic hazards, including storm surges and extreme rainfalls, which can produce acute impacts with long-lasting consequences. The interaction of multiple hazards often results in compound risks that exceeds the effect of individual stressors. Thus, immediate climate impacts affect long-term coastal vulnerability by causing cumulative and often irreversible changes to physical landscape and human infrastructure. These events act as catalysts, accelerating shoreline retreat, rising saltwater intrusion, and damaging protective ecosystems such as mangrove and coral reefs. This diminished the coast's natural resilience against future, more severe and permanent sea level rise. Hence, understanding short-term exposure is essential for developing strategies to reduce long-term climate change vulnerability. The assessment of coastal vulnerability is an ongoing, multi-decade process that relies on an interaction between historical data and future projections based on climate-driven process modelings. While historical trends show the coastal erosion is already accelerated by human activities, as you may see in this photo, predictive scenarios suggest that this kind of threats will grow even more. Therefore, accurate future forecasts are crucial to strengthen coastal environment resilience. The nature of vulnerability is dynamic and complex and cannot be analyzed directly. Hence, any assessment of vulnerability is a predictive judgment. It predicts what is likely to happen and why. The analysis breaks down the details to the point where they can be understood and addressed. Coastal vulnerability assessment methods have evolved substantially over the past decades. Early approaches focused predominantly on the physical dynamic of shorelines, whereas more recent methods integrate socio-economic, institutional, and ecological dimensions. These recognize vulnerability not solely as a biophysical condition, but as a socially mediated phenomenon. Coastal vulnerability assessment should be contextualized and focused on a specific issue. It may use tools at different spatial and temporal scales across various regions. Spatial scales for assessment can be defined as global, national, regional, or local. A global evaluation of coastal areas enables the development of global policies. National scale studies identify high priority areas for reducing vulnerability and aim to provide coastal managers with a visual perspective. Regional scale studies can establish setback lines or hazard-prone areas to guide planning. This geographical approach helps identify hotspot or critical vulnerable areas that require priority attention and more localized evaluation. Several methods have been developed to assess coastal vulnerability related to sea level rise, either quantitative and qualitative. These methods are grouped into three main categories as follows. Indicator-based approach and index methods are considered the main tools for assessing coastal vulnerability to climate-related events. They rely on the assessment of various parameters using either quantitative or qualitative methods, often in combination. The approaches combine multiple indicators into a composite score expressed by indices that allow spatial comparison of vulnerability levels. Coastal Vulnerability Index, CVI, is the most popular index-based approach for assessing coastal vulnerability in a specific study area. It is calculated by the geometric average of different biophysical parameters, including geomorphology, shoreline change rate, coastal slope, regional sea level rise, mean significant wave height, and mean tidal range. Although widely used, the indicator-based approach and index methods may oversimplify complex processes. GIS-based vulnerability assessment underpin most contemporary coastal vulnerability assessment, allows spatial integration of diverse dataset and visualization of vulnerability hotspot by mapping hazard intensity, exposure patterns, sensitivity indicators, and adaptive capacity across coastal zones. However, these methods are data sensitive to spatial resolution, scale mismatches, and availability. The comprehensive system approaches allow interconnected analysis by combining multiple vulnerability indicators with expert and stakeholder judgment, along with geospatial analysis to improve adaptation planning. A few examples of such complex systems are predictive modeling, scenario-based approach, multi-criteria decision analysis, and participatory approaches. Predictive models and scenario-based approaches involve projecting future climate hazards, population growth, land use changes, and adaptation pathway to assess coastal vulnerability. Participatory methods enhance quantitative evaluation by capturing local knowledge, risk perceptions, and social vulnerability aspects that are hard to be quantified. This includes interviews, focus groups, participatory mapping, and community vulnerability assessment. As a result, adaptation strategies such as coastal defense, beach nourishment, wetland restoration, and ecosystem conservation seek to reduce vulnerability and manage coastal risk through structural, ecosystem-based, and governance-oriented measures. While hard engineering solutions provide immediate protection, nature-based solutions offer sustainable alternatives with ecological and social co-benefits. Strategic land use planning and managed shoreline retreat are increasingly recognized as essential components of long-term adaptation. To conclude, coastal environments are increasingly susceptible to climate change-related hazards whose impact depends not only on the physical structural resistance, but on the capacity of people to absorb their effects and recover from loss or damages. Coastal vulnerability is geographically dependent, reflecting the specific interaction among local geomorphology, climate drivers, and socio-economic structures. The synthesis of conceptual and methodological perspectives underscore the importance of integrated and interdisciplinary approaches of coastal vulnerability. Methodological assessment approaches range from quantitative expert judgment to quantitative data-driven models. Index-based method, such as Coastal Vulnerability Index, remain widely applied due to their transparency and scalability. However, advanced assessment increasingly rely on GIS-based spatial analysis, remote sensing, and probabilistic modeling. Persistent challenges include data limitations, uncertainty in climate projections, and difficulties in setting the appropriate socio-economic indicators. Addressing these challenges and understanding vulnerability is essential for enhancing the resilience of coastal systems and determining the relevant policies. Hoping that this information will be useful to you in the future, thank you for your attention.